Okay, so in this video, we are going to quickly go over, just as a refresher, some information about first and second order ordinary differential equations, or ODEs. There is also a PDF of this information on Canvas, so whichever format you prefer, just make sure you review this before class because we will not be going over this information in lecture. So for a first order ODE, if we have a differential equation of the form tau dx dt plus x equals constant ks times f of t, I didn't write it, but x is also a function of time here. So x is our variable and f is our forcing function. Then for the special case where f is a constant, so f of t is just a constant, big F, then the solution to this differential equation for x as a function of time is x of t equals x of 0 minus x infinity e to the negative t over tau. Be careful not to get your t's and your taus mixed up. Plus x of infinity. So this isn't a math class. We're not bothering to solve that differential equation from scratch. What we are going to do when we are analyzing circuits is get a differential equation in this form, and then we know this is the solution. Okay, so you don't actually have to do the work to find that solution. We're only going to deal with them in this form. And for circuits, x is usually going to be a voltage or a current. Whereas if you were doing, for example, a dynamics problem, x could be a position, a velocity, a force, or something else. But in our case, we're going to be solving for voltages and currents as a function of time. So to solve this, we will need to figure out x of 0, which is our initial condition, x of infinity, which is our final or steady state condition, and tau, which is our time constant. And we get that from the coefficient in the ODE. So you'll notice the way I have that ODE written, there is no coefficient in front of the x term. The coefficient there is just 1. So as long as I write my coefficient, so I write my equation in this format, then the coefficient for the derivative term is going to be equal to tau. So to solve this equation in the form I've written it here, I need to find these three things when I'm analyzing the circuit. For a second order ODE, what we have is a little more complicated. We have a second order equation of the form 1 over omega n squared d squared x dt squared, so second derivative of x, plus 2 zeta omega n dx of t dt plus x of t equals ks f of t. So again, I have a differential equation with some coefficients in front of my derivative terms, and then there's no coefficient in front of x, so that's just 1 times my forcing function. For the special case of f of t is a constant f, we have the solution to that equation. Again, you don't have to find this from scratch. We are giving this to you. If you get a differential equation in that form, then this is the solution. X t equals alpha 1 e to the s1 t plus alpha 2 e to the s2 t plus x of infinity. And you might look at that and say, whoa, where are my omega n and my zeta or my x of 0 like I had for the first order case? So in this case, we have an equation for S1 and S2. they are defined as functions of zeta and omega n. So that's going to be negative zeta omega n plus or minus omega n square root zeta squared minus 1. So big equation, but we know that because as long as we have our differential equation in this form, this coefficient gives us omega n since it's the only variable there, and then once we know omega n, we can calculate zeta using this coefficient, and then once we have both of them, we plug them in here to give us S1 and S2. So we know S1, we know S2. We don't know alpha 1 and alpha 2, however. In order to find that, we need two initial conditions. Two initial conditions. So not only do we need x of 0, we also need x prime of 0, or if you're writing it out the way I did above, dx t evaluated at t equals 0. I just hate writing it out like that because it's not as compact. So we need two initial conditions, and then we will have two equations with two unknowns, and we can solve for alpha 1 and alpha 2. So x of 0 gives us alpha 1 e to the s1 times 0, so that term is just 1, plus alpha 2 e to the s2 times 0, so again that term is just 1, plus x of infinity, so that gives us one equation. X of 0 equals alpha 1 plus alpha 2 plus x of infinity. We take the derivative of the whole thing. That gives us our second equation, x prime of 0. We're taking the derivative of this equation here. S1 alpha 1 plus S2 alpha 2. Again, we're plugging in t equals 0, so the exponential terms just become 1. And since x of infinity is a constant, that goes away when we take the derivative. So there we have two equations, and we can solve for our two unknowns, alpha 1 and alpha 2. So to solve that second order differential equation, we need our coefficients omega n and zeta, which come from, our constants omega n and zeta, which come from the coefficients of the ODE once we have it in that form. Again, we need x of infinity, our steady state solution, and then we also need two initial conditions, x of 0 and x prime of 0. So we will be using these in class, but again, once you analyze a circuit and get an equation in this form in this class, we can assume, as long as you have that special case of the constant forcing function f, that this is the form of the solution.